Okay, and hopefully it should now move over to the laptop. Okay, right. So what we're looking at here is an example of a VAR. And let me motivate it. What I'm going to look at is the relationship between two key interest rates for the economy. Okay, I'm going to look at the relationship between bank rate and the treasury bill rate. So I've got two variables here, bank rate and treasury bill rate. Bank rate is the rate of interest set by the Bank of England, which the commercial banks can borrow and lend from the Bank of England at that rate. Okay, or sorry, borrow from the Bank of England at that rate. The treasury bill rate is the rate on short-dated government securities with a 3-month maturity, so a 3-month bond yield. So let me just, as usual, just take a quick look at the data. Okay, so what I'm going to do is just use the plot command here to plot the bank rate and the treasury bill rate. Sorry. Okay, and you can see that actually these interest rates are actually pretty closely related to each other. Okay, the blue line here is the bank rate. That gets changed fairly infrequently. The Bank of England announces changes in the bank rate, it's a regular monthly meeting. The red line is the treasury bill rate. That's a market rate of interest, so that's determined on a day-to-day basis by whatever treasury bill rates are trading at in the market. So you can see that changes much more frequently. Okay, so there's clearly a relationship between these series, and what I want to do is sort of try and capture that relationship by using a vector autoregression. Okay, so I want to model it with a vector autoregression. So how could I do that with eViews? Well, if like most eViews procedures, we set up an object to deal with this. So I can go here to Object, New Object, and one of the objects here is a VAR, Vector Autoregression. So I'm going to click on OK there, and it gives me a number of options here. But basically, what I've got to do is provide it with a list of variables that enter into the VAR. This does actually illustrate an important point here. For the most part, when we have a VAR, every variable in that VAR is an endogenous variable because they're all linked together. There isn't that clear distinction between endogenous and exogenous variables that there is in standard econometric modelling. So for a VAR, we just provide it with a list of endogenous variables because they're both linked together. Okay? So what I'm going to do is type in that box the variables in this VAR, which are bank rate and treasury bill rate, TBR. Okay? And then it automatically here puts a constant in as an exogenous variable, C, and it asks us what lags to put in. Well, it set a lag here of 1 to 2, indicating it will put 2 lags on each variable. I'm just going to, for the sake of comparison, leave that at 1 lag. So I'm going to set that at 1 there, and then hit return. Okay. So this is what it does when it estimates a VAR with that specification. Basically, it's estimated 2 separate regressions here. One where it's taken bank rate and it's regressed that on a constant, lag bank rate and lag treasury bill rate. Okay. The other regression, it's regressed the treasury bill rate on a constant, lag bank rate and lag treasury bill rate. It gives us the usual type of regression outputs here. It gives us coefficient estimates, standard errors in parentheses here, and then t-ratios below that in the square brackets below. Okay, so we can get some idea of what the structure is. You see actually that just about everything here is significant. Okay, we've got a bank rate is it's lag bank rate is significant in this regression, it's significant in this one, and lag treasury bill rate is significant in the first regression, it's also significant in the second regression. The R-squareds are pretty high, 0.98 for each one. Okay, so it's actually capturing the relationship quite well. Okay, we've got quite a good fit to the data at least. Actually, for the most part, we don't typically look at the raw VAR output like this. And often, if we've got lots of lags in the VAR, it becomes increasingly hard to interpret it. Okay? So for example, let me just show you one of the pitfalls here. If I was to put in a lot more lags, then the number of coefficients I would estimate would expand considerably. Okay? So if I was to go back to estimate here, okay, and instead of putting in just one lag, I'd put in 4 lags. Okay, you can see that my VAR now contains a whole lot more coefficients. Okay, we've got 4 lags on the bank rate, and we've got 4 lags on the treasury bill rate. Okay, so we've got, in a sense, we're probably over specifying this. We're allowing for far too many lags in here. Okay, so we generally want to be fairly economical about how many lags we put in. Okay, I'll come back to how we decide on that in a few moments, but what I'll do is just go back to my original model now and then talk a little bit about how we interpret it. Okay, so I look at that and think, well, actually most of these lags are completely insignificant. You can see that from these T ratios. So let's just go back to our original model here. Okay, and we'll, for the moment, that's the one that we'll settle on. Okay, so what I'm going to do is move back to the slides now. Okay, if I can. Sorry, main PC. I will do, as and when the technology will allow me to. Okay. Let me for the moment just shut this down, so stop recording. I've estimated my VAR. What I want to do now is trace out the effects of a shock to the system. What happens if there's a shock to either bank rate or treasury bill rate? How does that feed through into future values of bank rates and treasury bill rates? To do that using eViews, it's one of the standard bits of output of the VAR. It does all those calculations for you. If you go to View, you can click on impulse response here. Okay, what the impulse response does is it will trace out the effects of a shock to the system. You can display it either as a table or graphs or combined graphs. Personally, I find the graphs is the best way to display this. It's the easiest way to understand it. Okay, and it allows you to tell how many periods you want to solve this for, how many periods you want to use. Okay, now my data here is monthly data. So what I'm going to do is I'm going to set this for a period of 3 years, which will be 36 periods here. So I'm going to set that equal to 36. Okay, click on OK. And it will present me here with what we call the impulse responses. Okay. So how do we interpret these graphs? Well, we interpret these as giving us the response of each of the variables in the VAR to different kinds of shock. This first graph is the response of the bank rate to a shock to bank rate. So suppose there's a shock to the bank rate, we get an immediate increase in bank rate, and then over time it will decline down towards 0. You can see it takes quite a long time to do so. In this case, even by the end of 3 years, it's still not gone back to where it was before. Okay? The blue line is the central estimate. That's the central estimate of the impulse response or the dynamic effects of the shock. But because these are random models, these are random variables, this impulse response is itself a random variable. What we've got is the red lines showing us a 95% confidence interval around that central estimate. Okay, and you can see that if the 95% confidence interval doesn't include 0, then it is a significant effect. Okay, now this second graph here is the response of the bank rate to, let me go to this one first. This diagram here is the response of the Treasury bill rate to the bank rate. So we get a shock to the bank rate. How does that impact on Treasury bill rates? Well, what we get is an immediate increase in the Treasury bill rate, and then again that declines down to zero gradually by the end of the period. Now let's turn to these graphs here. These are the responses of the bank rates to Treasury bill rate. So we get a shock here to the Treasury bill rate. How does that impact on bank rates? Well, in the short run, the effect is zero because we've imposed that, we've assumed that. But then you fairly quickly get an increase in the bank rate in response to an increase in the Treasury bill rate, and then it declines off again down to zero. It has a peak effect here after about 6 months here. Okay? And then finally, we've got the response of the Treasury bill rate to a change in the Treasury bill rate, and that's showing us that we get an immediate effect that increases for the first couple of months, but then starts to decline after that. Okay? So VARs give us a way of understanding what the effects of random disturbances or shocks will be to this system of equations. So it shows us how it will react over time. And those reactions over time are what we call impulse responses. Okay. Can I just pause there and ask if anybody's got any questions on that? No? Okay. Right. Well, while I've got this up, I'm going to consider the other type of output from the VAR. Okay. Because the other chief type of output from the VAR is what we call the variance decomposition. What this captures is the effect of different kinds of shock in terms of how much of the variance of these variables that enter into the VAR is being explained by the different kinds of shock. Okay? So I think the easiest way to show you this is just to take a look at this example. We'll go back to it on the screen in a moment. Okay? So again, if I just click on the stats here, that's what I've estimated. Okay? I've looked at one type of output, which is the impulse response. Let's now take a look at the other type of output, which is the variance decomposition. So if I go to view, you see here the option here is variance decomposition. And again, we get a little dialog box here. We can look at it in different ways. Now with the variance decomposition, I find it easier to look at this in table form, because I'll show you why in a moment. It's easier to understand. So I'm going to click on that table option here, and then so that I get it reasonably on the screen, I'm just going to consider 12 months here for the variance decomposition, so 12 periods or 1 year. And if I do that, if I hit the return button there, this is the output it gives me. So the question is, how do we interpret this? Well, remember, what we've shown with the VAR is that the behaviour of each series depends upon random shocks to the system that occurred both in the current period and in past periods. What this does is tell us after how many periods, how much of the variance is explained or down to different kinds of shock. So for the bank rate, in the first time period, 100% of the variance of the bank rate is explained by shocks to the bank rate. Okay, that's because we had a coefficient of 0 on the Treasury bill rate in our bank rate equation. Okay, but then over time, because there's a moving average process going on here, it will the effects of shocks to the Treasury bill rate will start to feed through and will have an effect on the bank rate. So you see, after 2 months, 83% is still being explained by shocks to the bank rate, but 16.3 is being explained by shocks to the Treasury bill rate. And that effect actually builds up quite substantially over time. And by the end of 1 year, 73% of the variance of bank rate is being explained by shocks to the Treasury bill rate, and only 26.7 is being explained by shocks to the bank rate. So it kind of swaps round there, and the shocks to the Treasury bill rate are really quite important in explaining the variability of bank rates. Okay, if we scroll down a little, we can see the same results for the Treasury bill rate. Okay, Now for the Treasury bill rate, remember there's an immediate effective bank rate on Treasury bill rate here. The contemporaneous coefficient A21 is not equal to 0. So even in the current period, the variance of the Treasury bill rate is explained partly by shocks to itself, with 65% being explained by shocks to the Treasury bill rate and just over 34% being explained by shocks to bank rates. Then over time, you see that the Treasury bill rate shocks become even more important, going from 65% through to 80% after 1 year, with bank rate effects declining from 34 to 19.7%. Okay, so that's the other principal type of output we can get from a VAR, is the variance decomposition, which gives us the fractions of the variability that have been explained by the different kinds of shock. Okay, trying to capture how important these different kinds of shock are in generating the data. Okay, has anybody got any questions on that?